Shall I start, sir?
Yeah, please start. Please start.
Pleasant good morning to one and all. On behalf of EEE Department, NIT Puducherry, on my own behalf, I welcome Dr. S. Kumaravel from NIT Calicut for the Atal workshop. Welcome you, sir.
Yeah, thank you.
Okay, fine, sir. It is my immense pleasure to introduce our today's guest for our Atal workshop. Dr. Kumaravel Sundaramurthy has been working as assistant professor in the Department of Electrical Engineering, National Institute of Technology, Calicut, Kerala since December 2008. He has acquired BE in EEE under Bharatidasan University, Tiruchirappalli, and also MTech in Power Systems from National Institute of Technology, Tiruchirappalli, and he has completed his PhD in Electrical Engineering from National Institute of Technology, Calicut, Kerala. Also, he has completed postdoctoral fellowship in the area of power converter applications in power systems from University College Dublin, Ireland. His major areas of research are design and development of DC to DC converters, stability enhancement of microgrids, solid-state transformers, etc. As on July 2020, he has published 23 research papers in SCI journals, including 5 IEEE transactions and 4 papers in IET Power Electronics and several papers in reputed IEEE international conferences held in India and also the abroad. He has supervised 5 PhDs and 30 MTech scholars. He has applied 2 patents and another in pipeline in the area of non-isolated DC to DC converters. He has completed 2 sponsored research projects and involved in the development of real-time simulation lab and distributed generation lab in NITC campus. Currently, he has 2 ongoing projects with the approximate cost of rupees 0.75 crore from MEITY, CSIR, and NAMPET 3. He has received awards such as Young Research Fellow from the Ministry of IT, Government of India, which includes the monthly fellowship of rupees 20,000 for 5 years. Young Scientist Award 2017 for engineering stream from KSC STE, Government of Kerala, Outstanding Branch Counselor Award 2018 from IEEE Kerala section, IEEE PES chapter Outstanding Engineer Award, etc. He is a senior member of IEEE, the member of ISTA and Institution of Engineers. Once again, I welcome you, sir. I just hand over the session to Dr. S. Kumaravel. Thank you.
So, very good morning to all of you. Thank you very much for your introduction, Mr. Yuvan Raju. So, I hope that most of you are working related to power electronics. The title of today's presentation is Power Converters for Electric Vehicle. So, as you all know, the demand on electricity increases day by day because most of the country moving from underdevelopment towards development, developing towards developed, so that the life index, human life index, increases every year. So this index primarily decided based on the annual energy consumption, per capita energy consumption. Whereas country like a developed nation like US, Singapore, their per capita consumption is always greater than 2,000 or more than 3,000, or some countries they reached closer to 4,000 and above. But whereas country like India, just we have crossed 1,000 unit per capita consumption. I hope just 5 or 6 years before. So though we called as a developing country, MNRE says more than 18,000 villages are not even electrified yet. So though the gap between energy demand and supply widening year by year, I think almost 8% gap already exists between demand and supply. So apart from these problem, the major problem entire world is looking into the fossil fuel. So these fossil fuels are highly site specific, and moreover, the cost also increases year by year. So such a intermittent nature of or maybe the dynamic nature of pricing lead towards the alternate technology. And another main problem is global warming. So because of the security issue in terms of economic security issue and global warming lead us towards the energy extraction from renewable energy sources. So though one aspect we talk about the electricity generation from the conventional resources such as thermal, hydro, nuclear, even then we are facing lot of socio-economic problem. So in the past 15-20 years, Kudangulam power plant was one of the main project launched by our government of India. Fortunately, they succeeded after facing a huge social problem. So one end, this fossil fuel, another end, commencing atomic power plant, also the hydro plant, we have almost reached the saturated capacity. So we are in the position to move towards the new type of energy sources such as solar PV, wind, etc. So when we talk about the renewable energy sources, solar PV and the wind, these are the two leading technology currently we look. So this one and this one we see. So in terms of this hydro, we are looking into micro hydro and pico hydro. Micro and pico. So when you see micro and pico, especially the Western Ghats region, like our Western Ghats region of Kerala, we have enough potential to generate electricity in terms of less than 10 kilowatt or maybe 10 to 50 kilowatt. So that type of small power plant can electrify some cluster of houses. You all know that even today there are places in Wayanad district, they didn't receive electricity. And moreover, especially in Kerala, extending existing grid become costly affair. And on average, the cost per meter is 10,000 rupees. So just if you lay some pole and some transmission line, that requires 10,000 rupees per meter. So that is another reason why we are not going ahead with the conventional grid, especially the hilly territory, especially in the Wayanad places and other places. So rather promoting the conventional electricity based powering system, why don't we move into renewable energy sources? That type of studies started, and as I already said, there are enough potential to start power plant in terms of micro hydro and pico hydro in some of the places. You all know that we depends upon the conventional resources. So when you try to see the conventional resources, we are in the position to integrate these energy sources using a grid. So that when you talk about a grid, it is something like...
Hello, sir.
Yeah, please.
Hello, this is Yuvraj, sir. Sorry for interruption. Your slides are not visible, sir.
No, I only change the slide. I am opening paint. Okay, sorry. I
Okay.
myself
Okay. Fine, sir.
used the presentation. I want to write something, so I'm moving into PowerPoint.
Okay. Go
Okay.
ahead, sir. Thank you, sir.
So when you try to talk about the integration of the conventional energy sources, as I pointed out, so when you see the conventional resources, for example, assume that you have a coal power plant here. Assume that this is a coal power plant. And you all know naturally the capacity of the coal power plant usually in terms of 1000 megawatt. 1000 megawatt. And when you see the other side, you can have a atomic power plant. So that atomic power plant hardly 500 megawatt or maybe equal to the thermal, equal to the coal power plant, maybe this much capacity. So when you see the other side, hydro power plant, maybe in the same scale, something like this. This also in terms of some 200 megawatt. So when you try to see these generators, in general, these generators are generating electricity in terms of 11 kilovolt. This is 11 kilovolt generation. 11 kilovolt generation. This also 11 kilovolt generation. So when you have this 11 kilovolt generation, you all know how we integrate. We integrate using a step-up transformer. So these step-up transformers form a ring main system. These step-up transformers form a ring main system. So according to the place of utilization, so these ring main systems are taken to substation level. So there we are trying to use a step down transformer. For example, this 11 kilovolt transmission line, we take a tap. From here, we take the power of something like some small transformer of maybe 110 kilovolt or 11 kilovolt, and then we go ahead with a short distribution. Again, we'll go ahead with one more transformer, and here we use 11 kV bar 400 volt, and then we have load. So what I am trying to conclude here, at present we follow a ring main transmission system and a radial distribution system. So this is nothing but your ring main ring main transmission system, whereas this is called your distribution system, which is radial in nature. So when you try to see the total system involved in integration of these sources and this load, everything together called as a grid. So when you try to see the grid, two major process this grid is doing. So when you talk about this load point of view, the real power and the reactive power changes in its own direction. So when the demand of P and Q varies, which is dynamic in nature, P of T and Q of T. So according to with respect to time, these two will vary. It is not constant always. So according to the variation of P and Q, always there is an impact on the grid in terms of voltage and frequency. So when there is a variation in P and Q, we control this frequency as well as voltage using two major devices here. One is called AGC, automatic generation control, Another one is called AVR, automatic voltage restorer, and these two are naturally available in the generation station. These are available in the generation station. So apart from that, naturally we have these transformers as OLTC transformer. I think all of you may be aware about what is OLTC transformer, online tap changing transformers. So in order to control or maybe match the real power as well as the reactive power demand, we always cope up with voltage and frequency. So that is the main duty of grid. So grid is a big network which receives power in terms of standard voltage and frequency and transfer that power to the load with respect to the demand in real power as well as reactive power in terms of the specified voltage and frequency. So when there is a change in real power and reactive power, the parameters in the generation side varies, like frequency, transmission voltage varies. So we are in the position to control those things. So far these are the main duties we carried out. But after integration of the so-called renewable energy sources, so now you can imagine where these renewable energy sources are coming. These renewable sources are coming near load. That is called on-site generation. That is called on-site generation. So wherever you have load, there itself you generate. That is called on-site generation. Sometimes we call it as a distributed generation. Sometimes we call it as a distributed generation. So when we try to go for on-site generation, so there also the same phenomenon is coming to the picture, but this is called a global parameter, and this local load with the local source called as a local phenomenon. But anyhow, when there is a source, when there is a load, when these two are integrated, we have to follow the grid profile. I already told you what is a grid. Grid is performing the duty of transferring power from source to load. But that grid is a macro grid. The grid, what I mentioned, is called local grid, because there is a source and there is a load. These two are situated together as a small system. So that is called a microgrid. So now you all understand why do we go from macro grid to microgrid. Why do we go for macro grid to microgrid? This is a microgrid and this is a macro grid. So macro grid receives energy in terms of several megawatt, 200 megawatt, 1000 megawatt, and transfer that through a long transmission line. Lot of devices involved in that, in terms of protection, in terms of operation, like fax devices and all put together to regulate the real power as well as the reactive power. Then we receive near the local sender, that is called a load sender, and then we power the devices. Such a tricky system the macro grid system is. So as I pointed out, a local source, local load put together as like a small grid. Now whatever you are seeing here, this is a small grid, and this small grid is called as a microgrid. Small grid is called as a microgrid because there is a local source and there is a local load. This is a local load and there is a local source. Why I am particularly talking it as a grid? Because the real power injection varies here. According to the real power injection, this guy utilises this reactive power, utilises the reactive power. Similarly, this guy also, it utilizes the solar radiation and injects the real power. And this guy, it varies according to charging and discharging process. It may be plus or minus. So what I am trying to say, though we have sources which are not schedulable in nature, because it's renewable energy sources, you can't schedule it. And here also you can notice utility grid is there, but whereas every load receives power as well as reactive power. So here also it receives real power, reactive power, real power, reactive power. So generally speaking, you can call it as P1, P2, etc. So if you put together everything, so P from renewable generation plus R minus P utility grid will be always equal to the load P load. So this phenomenon is strictly followed in our microgrids. So what is a major problem here? Because this is not constant. This is not constant. And this is also not constant. This is also not constant. And another sensitive problem is the X by R ratio. In the case of a microgrid, the X by R ratio is very, very less. Uh, the X by R ratio is something like we have how to undo it. So when you see the impedance of a short transmission line, it is always lesser in nature. Lesser in. So especially the total circuit is highly resistive in nature, so that compensating the reactive power as well as real power was quite all right, especially in the long transmission line. I think you all may be knowing what is happening in the long transmission line. Long transmission line. Because naturally, whatever may be the inductive reactance and capacitive reactance we get in the long transmission line, one to other always compensate. One to other is always compensate. So the value of X become low, so that, and when you see the whole X by R ratio, so this is low, this is high, so it is very, very less in the case of long transmission line. In the case of long transmission line, because the value of X is very, very less. But whereas in the short transmission line, what is taking place? In the case of short transmission line, what is taking place? In the case of short transmission line, the main problem is from this guy. So we don't have any compensation here in the short transmission line. We don't have any compensation. So this compensation is not possible because there is no custom power devices available in the microgrid structure. There is no custom power devices available in the microgrid structure. So the value of X is very, very higher than R. The value of X is very, very higher than R. So naturally what happened? This value is always high. So naturally these type of grid are called as your weak grid. Now you can understand why I am calling this grid as a weak grid. Why I am calling it as a weak grid? Because whatever the transmission or impedance created due to this impedance become very, very low. It become very, very low. So the X by R ratio is very, very high in the case of a weak grid. So that when you try to integrate the so-called local resources in this nature, so the current through these highly varies according to the nodes. And that too, after integration of electric vehicle, you will understand major severity what we are going to face in the case of macro grid. In the case of a macro grid. So that is an alarming situation. What we are going to do after integrating electric vehicle into the microgrid system, because large amount of electric vehicle are yet to be connected in this weak grid. So by the time, what is going to happen? What is going to happen? That ultimately is going to create a very big challenge in the future system. So when you try to go to any integration of renewable energy sources, we always depends upon renewable energy sources. The power converters. Whenever we go for power converters, there are different power converters we use according to the nature of supply and the nature of load or maybe utility interface. Especially in the case of solar PV, we prefer this DC to DC converter because of MBPT tracking. So whenever we are going ahead with this MBPT tracking of solar PV system, we go ahead with the DC-DC converter. Of course, inverter also can be used to track maximum power point, but maximum flexibility you will get in the DC-DC converter. Because you all know that the operating duty ratio will never be equal to the operating range of modulation index in the case of inverter. So we always prefer a DC-DC converter for effectively tracking maximum power point in the case of solar PV system. Another issue you all know that partial shading. So partial shading is another one of the unanswered question even today. Partial shading is another problem in the case of the renewable energy integration, especially solar PV. So whenever you talk about this MPPT and this partial shading, we always going ahead with a DC-DC converter. So you all know that from 1887 onwards, we started using AC in generation, transmission, distribution, utilization. Everywhere it was AC. In late 20th century, that too 1980s onwards, when power electronics are started in terms of thyristor and other conventional devices, HVDC came to the picture, especially for the transmission. HVDC transmission become very popular. Especially in countries like India, there are many tie lines are made between different regions to improve the stability of the grid in terms of HVDC system. So again, HVDC in higher level also started coming, especially in countries like India. So when you try to see the overall system of our power system structure, everywhere we started using the AC as well as DC. I think all of you may agree with me, because we can't go ahead only with the conventional power electronic system, right? So whenever you go ahead with the conventional system, definitely we fail to provide a reliable and efficient energy system. So when you try to investigate the total power system, I already pointed out that conventionally these things are something like conventional sources, where only in terms of DC or maybe AC. Conventional sources I'm asking. So these conventional sources always AC in nature. All the conventional sources are AC in nature. But now, due to the technology development, we started integrating these so-called renewable energy sources, something like this. We started integrating these renewable energy sources, especially solar PV, etc. This is a solar PV system. This is a solar PV system, and this is conventional system. This is a conventional generator. This is also a conventional generator. This is a conventional generator. So what I am telling you, in conventional method, we use alternator, so-called alternator. So these alternators were quite all right. Now, when you try to integrate these renewable energy sources, we depends upon this power electronics. So as I already pointed out, either this a DC converter, and then you have an inverter. Then we are integrating with grid. So this is the structure we follow when you try to integrate with the grid. Assume that this is our integration we made like this. So what I am concluding here, all the generation technology, we started using power electronics. Generation, we started using power electronics. So as I already told, renewable sources like solar PV, wind, we started using power electronics, especially in wind sector. This DFIG, double effect induction generator, become more popular. There also we started using power electronics. So what I am concluding here, the whole generation system started including this power electronics. So when you try to include power electronics into the generation, naturally what is going to happen? The linear source is going to become a non-linear source. Linear source is going to become a non-linear source. So why I called conventional alternator as a linear source? Because it is made up of RLC element. It is made up of RLC element. But now, after bringing this power electronics, it is going to become a non-linear element. Now you all know how to handle linear system, how tough to handle non-linear system. So now coming to the transmission, previously the transmission was occupied by transmission, that is nothing but your transformer. There is a transformer here and there is a transformer here, here and here. There are transformers alone. But now what happened? We started integrating fax devices. We started integrating these fax devices. So naturally, what is this fax device? Again, power electronics. So so-called generation also become non-linear. Now the transmission line also become non-linear because we started using power electronics. Coming to the distribution, currently we use a distribution line of radial system which is linear in nature. But in the near future, all these conventional transformers will be replaced by a solid state transformer. I think all of you know what is called a solid state transformer. The solid state transformer is also become power electronic based transformer. As I told, source become power electronics, generator become power electronics, transformer become power electronics. Now one more thing is there called transmission line. So currently we have wired transmission line. So what is the prediction about transmission system? Definitely in another few years we will try to find a technology to transfer electricity without wire. That is called wireless power transmission. Maybe now the research work is going on in terms of few micrometer to few meters, but definitely there is no doubt in the near future we will achieve a suitable technology to transfer power in terms of several kilometers what currently the transmission lines are utilized. So what I'm going to say, the whole power system is going to be revamped full of power electronics. So whenever you use the term power electronics, the linear system will be changed into a non-linear system. So handling linear system is much simpler. Handling non-linear system is very tough. You all know what are the properties of linear system, what are the properties of non-linear system. So when this type of situation arises at present, so with this moment we are moving towards our so-called electric vehicle. This I already told you what is called this renewable energy. So now I am going to cover a DC-DC converter, particularly for renewable energy source, especially for electric vehicle application, because we rely on battery to store electricity. So whenever you use a DC-DC converter, so we sometimes use this source as our input source as your battery, and this output source may be your drive, the drive system, your drive system. So when you try to have a source and load, we need a DC to DC converter to convert from one power level or one level of voltage to other level of voltage. So according to the application, we go for either non-isolated category or isolated category, according to the application again. So some application recommend non-isolated converters, some application prefer isolated converters. It depends upon the application. So generally, any DC-DC converter can be classified into two types. One is non-isolated type, another one is isolated type. So this is the best example of non-isolated type DC-DC converter, conventional buck converter. So first of all, why this is called as non-isolated DC-DC converter? You all know what is the circuit of your buck converter. So when you have a buck converter, this will be our diode, and you have a filter here, followed by a load. This is the schematic diagram of our conventional buck converter. So there is a switch, inductor, diode, and a capacitor. And this is your V in, this is your V in, and this is your V out. So when you see non-isolated, the negative terminal of input and the negative terminal of output, both of them shares a common wire. What it means, whatever the potential it contains, this is remaining same with respect to your ground, because we take zero potential here, zero potential here. So what are the advantages you are going to get here? So whenever you use non-isolated DC-DC converter, the so-called leakage current become very, very zero. Leakage current is almost zero in the case of the non-isolated DC-DC converter. But what is the demerit here? The source and load are not isolated. Source and load are not isolated. So if it is not isolated, what is the problem? Assume that there is a surge here. Assume that there is a surge here. Assume that there is a surge here. So when you have a small surge in the other side, so that surge definitely propagate into the source side, and that hits here. Assume that there is a surge here, and I said that there is surge here. This surge easily can propagate back into the system, so that your source also will damage sometime. So another problem is the protection. So you have to provide protection throughout the element in terms of source as well as in terms of load, because naturally the fault may be arises from any point of time. So if you are not providing proper protection, you can't separate the healthy system from the fault. So these are, so that naturally the cost of the system increases in the case of a non-isolated DC-DC system, especially in protection point of view. So now let us see what is called the isolated system. This is the best example of isolated system. There are different isolated DC-DC converters, whereas here the isolation is provided in terms of alternating current. This is a high frequency alternating current. So whereas in some circuit, especially you all know what is called a flyback converter, right? You all know what is called a flyback converter. Flyback converter is also called as an isolated DC-DC converter. Flyback converter is also called as an isolated DC-DC converter. So that flyback converter isolation is provided in terms of DC. So there, that inductor is called as DC linked inductor. DC link inductor. DC link inductor. Whereas in AC, we call it as a high frequency transformer. We use the term transformer, high frequency transformer. So the main advantage what you are going to get here, so this ground is different and this ground is different. So whatever the protection or whatever the fault coming out from this side will be completely galvanically isolated with the help of this transformer. That is the main advantage what we are going to get from these isolated DC-DC converter. So naturally, in most of the PhD thesis or MTech thesis, what naturally our students are doing, without understanding the system, they are straight away going to implementation or designing the controller. So what they are doing, they take some power converter and then they do simulation in MATLAB, and that too using Power GUI. You all know what is called Power GUI, Power System Graphical User Interface, and directly they do simulation in variable step size, and they assume that whatever the result they got are correct. Sometimes they write conference paper with respect to the simulation result. Sometimes with a few hardware, they go ahead with the Scopus or SCI journal. In my opinion, that is a wrong practice. If you want to become a perfect power electronic engineer, first of all, you should know what is the open loop system meant for. Assume that this is your buck converter. You have to treat this as a system. So when you talk about a system receives n number of inputs, x1, x2, etc., xn. At the same time, this system produces m number of output, y1, y2, etc., ym. So this system produces m number of outputs and n number of inputs, so that the system, whatever you are going to see, become a multi-input, multi-output system. Practically speaking, especially in power electronics, most of the system belongs to multi-input, multi-output system. Without a proper investigation of the system, it is not fair to design a controller. Frankly speaking, most of the product operated without a controller. So you have a system, you all know what is a controller, right? You all know what is a controller. So whenever you go for a controller, especially you know what is a control. When you try to take a system, assume that you have a system. This is your system, and you take input of a system, and then it produces output of a system. So this is related by a transfer function y of s by x of s, and you have some zeros here, that is called s plus a, something like this, and you have poles s plus y, s plus x, something like that. So we investigate stability of the system using this characteristic equation, using some tool. Either we go ahead with Nyquist criterion in the closed loop system, or maybe simple Bode plot. We see what is the phase margin, what is the gain margin. According to that, we infer the stability of the system. My question: if system itself naturally stable, then why do you need a controller? I am telling you, you take a simple buck converter. If you investigate closely the transfer function of a buck converter, if, for example, you take output voltage versus maybe the duty ratio, the transfer function will be look like this: s plus a or into some gain divided by s plus x into s plus y. So now tell me, the system is stable or not? This is a typical transfer function of a buck converter. Can you please tell me whether the system is stable or unstable by seeing the transfer function? I think for the past 45 minutes I am alone speaking. I am not getting any response from participants. I don't know whether they are there in line. Can you please respond me through chat box? I'm just putting transfer function of a buck converter. I'm asking the question: is it stable or unstable? Yeah, stable. Yeah. So when you try to see stable, my question: if the system itself is stable, then what is the necessity of a controller? What is the necessity of a controller? Shall we go ahead with the open loop system? So shall we go ahead with the open loop? You all know what is called open loop system, right? So this is a typical example of a open loop system. So this is a open loop system. Yeah. So I am telling you, system is perfectly stable. Then why do you need a controller? Yeah, I think K.S. Ravi Kumar told dynamic performance improvement. Dynamic performance improvement. Okay, let me see what is called the what are the improvements we can do here. Yeah. So when you see here, this is a second order system. You all know what is the response of a standard second order system. So response of a standard second order system will be like this. The response of a standard second order system will be something like this. So when you see a standard response of a second order system, it will be like this. So there is a rise time, there is a rise time, and there is a overshoot here, there is a overshoot. Sometime, if this is your reference, assume that this is your reference, there may be a steady state error. Assume that this is your reference, and there is a possibility of a steady state error. Okay, so I'm telling you, you have a target of PR should be this much. For example, assume that it should be 0.2 seconds. It should be 0.2 second. Your percentage MP should be less than 10%. And assume that your steady state error is plus or minus 5%. So what I am asking, in your operating region of V0 plus or minus V minimum and V maximum, if converter itself naturally gives the expected performance, what is the necessity of a controller? No need. That's what I am stressing particularly here. It depends upon the application. It depends upon the application. You all know how tough to implement a closed loop system. First of all, if you want to go for a closed loop system, you should need a feedback. Suppose if you convert this into a closed loop system, what do you want? You need a sensor. So this is nothing but your feedback system H of S. Then you should go ahead with your comparator. This is your comparator. This is your negative feedback, and you give a reference here, V reference. Then you have to go ahead with a controller selection. Selection of controller is also not easy thing. You can select PI, you can select PID, you can select PD, you can select nonlinear control like a robust, like a model predictive control. Like that, n number of choices are there. Which control technique you will select? A big question mark. Then, is it a one parameter control or multiple parameter control? Because in most of the power electronic system, we have outer current control system, inner voltage control system. That's what I'm mentioning. Sometimes we may have to provide more than one controller. So then we go for the control generation of control signal, and this will become finally a control signal U. My question, if your application does not require all those complex systems, they much bother about the cost of the controller, then why do you go for the controller? No need. That's what I'm telling you. It depends upon the application. It depends upon the application. This factor decides whether you need a controller or not. Otherwise, you can go ahead with your simple open loop system. You can go ahead with your simple open loop system. A lookup table is more than sufficient. Your lookup table is more than sufficient, right? A lookup table is more than sufficient without a controller, because no need of any feedback. No need of any feedback. So when you try to see application, Then if application specify that I want the overshoot should be less than 2%, and I should have the steady state error of tightly 1%, and assume that the raise time should not greater than something like it should be something like zero point 0.2 millisecond. So it depends upon the application. Again, I'm telling you, it depends upon the application. So according to your application, you can go ahead with a controller. But my question, as an electrical engineer, do we design a controller properly? Never. Never design. What we do, simply we take some trial and error basis, some KP, KI, and we go ahead with the system design. That is absolutely a wrong approach. Absolutely a wrong approach. That we should never do on the power electronic system. So properly speaking, you have a power converter. You know what is your power converter. Then whatever we do only a steady state analysis. And that itself is wrong. So we have to go ahead with dynamic model of the system. Including system parameter. So you know what is called a system parameter. For example, if you take a simple buck converter or boost converter, we take these something like this. So especially in this power converter, what are the parameters we eliminate? Assume that this is my simple boost converter. What are the parameters we eliminate here? First one is this source resistance. So technically speaking, you all know the source resistance is always exist in any practical system. You can think that, sir, the source resistance is only 0.1 ohm. Shall I neglect? Never. Assume that your current is something like 100 ampere. The power or voltage drop of this 0.1 alone is 10 volt, and the power dissipation is 100 square into 0.1. Now you can imagine how sensitive this 0.1 ohm resistance in power electronics are. So we neglect that, source resistance is 0.1 ohm, we can neglect. It is not, we are not supposed to leave the resistance of source. Second one, the resistance of the inductor. So every resistance will offer a resistance something like this, every inductance. So when you investigate, hardly a 5 millihenry inductance can have 10 milliohm, 0.01 milliohm. When you talk to this switch, ideally speaking, there is no forward voltage drop, that is drain to source voltage drop. There is no on-state resistance, and we assume that the switch is ideally turn on and turn off. When you say turn on and when you say turn off, it's not like this. In any practical system, if we say a turn on process is always like this, and this is in terms of current. If we say the voltage is in terms of like this. So always there is a small forward voltage drop, always there is a small losses due to switching. So forward voltage drop, on state resistance, then switching also play a major role in deciding the converter performance. Similarly, when you talk about this diode also subjected to forward voltage drop and the on-state resistance and the reverse recovery loss. And similarly, capacitor, again parasitic ESR of the capacitance, that is also playing a major role in deciding the converter performance. Apart from all these parasitic elements, there are stray inductances and stray capacitances due to the connecting wires or PCB board. So technically speaking, every power power converter is operated with the switching frequency of 20 kilohertz or maybe 100 kilohertz. So whenever you go ahead with a large switching frequency, so naturally the effect due to stray inductance and stray capacitance become more. Stray inductance and stray capacitance become more, so that the total converter performance get be degraded because of this. So now you can understand what I am trying to convey. So whenever you design a power electronic circuit, you have to go ahead with power converter, steady state, rather going to steady state analysis, you have to go to a dynamic model, that too a small signal model. So after looking into a small signal model, you have to go ahead with the significant transfer function, sometime V0 by D cap, sometime I0 by D cap, sometime IL by D cap, sometime V0 by Vs. All sort of transfer function you have to take, because though you are trying to control the either current or voltage, naturally this also may happen due to load side disturbance. And sometimes V0 by I0 also we have to investigate, because load change happens. So what I'm trying to say, finally you have to treat the whole system as a MIMO system, and you have to perform variety of analysis. You have to perform variety of analysis. Then only you can design an effective controller. Then only you can design an effective controller. So now you can understand what are the seriousness we should give, especially when you design a converter. So why we move on to electric vehicle? I think some people might have already given introduction to electric vehicle. So I'm moving this slide. I'm moving towards electric vehicle. So you all know that electric vehicle is going to play a major role in the near future. So electric vehicle is concerned, the major portion is source. This is your source. So this is your source. That is nothing but battery. Nowadays people started using lithium ion battery. So you have a drive. This is nothing but your drive system. So this is your motor with a drive. So this is your drive system. Then you have a power electronic system, and this is your power electronics. So what I am trying to say, the major portion involved in the source and this power electronics and the drive. So these three are going to decide the total performance of a system. So in electric vehicle, we go ahead with hybrid system. Why? Because first of all, we want to provide a reliable power. So if it depends only on battery, you can't provide a reliable power. So you have to go ahead with additional sources like a primary, secondary sources. So second one, something like a low cost electricity. Low cost electricity. Because whenever you try to see a portable devices like battery, you can charge this battery from different utility. So one, you can directly charge it from grid, utility grid, and something like a solar PV, and something like a wind. So you have variety of charging facility to this electric vehicle, so that according to that you can go ahead with charging. Then you are going to provide mileage. So whenever you see the electric vehicle, operating region of the vehicle is going to decide the total cost of the mileage. So I'm telling you, when you power battery, the cost is different. When you power this fuel cell, cost is different. And to balance these in transient, you are going to provide capacitor. So this is going to be a mixture of renewable energy sources or non-conventional energy sources. So when you try to power up, you are going to use a dedicated DC-DC converters. So in my research, we concentrated on the development of a non-isolated multi-input single output DC-DC converter, that work I am going to show. I hope the time is hardly 11 o'clock. We have another half an hour. I am looking into the some research perspective what we are currently doing at NIT Calicut. So when you try to see the conventional system, as I mentioned, here we have taken the sources as solar PV and battery. These are the two sources we have taken into the picture. So, as I said already, you are going to use a DC-DC converter. This is unidirectional, and there is another DC-DC converter. This is bidirectional. Means this converter acts as boost when the power goes from here. This acts as buck when goes from here. So the problem what you are going to face here is utilization of two different converters. So rather going to use such two converters, why don't we replace it by a single converter? That is our research objective. Our objective of the research is to replace these two converters by a single DC-DC converter which integrate both battery and solar PV to the load. That is the research objective what we have framed here. So we have derived a converter structure so that these converters, that's the novelty of the converter, this converter structure integrates source 1 as well as source 2 using 3 switches, 1, 2, 3 and 1 diode. So we are going to use only 3 switches, 1 diode, 1 inductor, 1 capacitor. So 2 reactive elements and 4 active elements. So the total component become 7. So using 7 component, we are going to integrate 2 different sources. Not only that, the same converter structure can be operated at 6 different modes. What are the 6 different modes? Power can go from source V2 to load. Second one, V1 to load. Third one, V1 to V2 to V1, because V1 is always unidirectional. V1 is always unidirectional. Like a solar PV, this is solar PV. V1 can be your battery. So this is bidirectional. So third mode, this power is feeding back to your battery. So fourth mode, bidirectional, reverse power flow. Assume that regenerative braking. Assume that when there is no, when there is a regeneration here, and this power can be feed to your battery. That is called a reverse generation, right? Reverse power flow. That's a fourth mode. Fifth mode, assume that battery is full. You have a power from solar PV. So when the vehicle is connected to utility grid, this battery power can be pumped to your external supply. So sixth mode, charging this battery from utility grid when there is no solar PV available in the night time. So what I am concluding here, a single converter using 7 components, that two reactive plus 4 active. Sorry, I think 1, 2, 1, 2, 3, 4. Sorry, this is 6. Using six components. Using 6 components, it is going to perform 6 modes of operation. That is one of the main attraction of the proposed DC-DC converter. Second one, as I already mentioned, both the source can power up so that it can act as a complement to each other. So since we use only 6 components, so it is going to have low component count, lesser weight and low cost. These are the attraction of our proposed DC-DC converter. So all the 6 modes I am explaining here. In solar PV powered mode, it acts as a boost converter, boost, buck and super boost. So though there are 6 modes of operations, it is going to be 1 together, and this is 2 together, and this is 3. It is going to perform only 3 type of operation using the whole structure in control system perspective. I think already I said what is called a control system perspective. So though I have a control converter structure, I can analyze the performance of the converter when it operates as a boost, when it operates as a buck, when it operates super boost. So I can have the 3 state space model, 3 state or small signal model. And I can investigate all the performance. And another beauty, though I am going to use 3 switches, you can see each type of operation actually only one switch only involved. And of course, here and here, 2 switches are involving, but each mode of operation you can see only one switch will be involving. You can see here only one switch is involving. I think only one mode of operation, I think all the modes of operation, only one switch will be involved. That is an ultimate advantage of our proposed DC-DC converter. This is the operation of the converter in super boost mode. Super boost mode says that this inductor L will be charged by V2 first. Here, sorry, out of V1 and V2, we assumed that V1 is greater than V2. So V1 charges first, followed by V2, and then it goes to the discharge. Like that, we have formed switching sequence, and we assume that the current is in continuous conduction mode. So it is going like this. So the final output voltage termed as V0 by V1 D1 into 1 minus D2 by 1 minus D2. This is the overall output voltage equation. So main advantage here is that in the super boost mode, so the per unit output voltage can be enhanced to this level compared to your conventional DC-DC converter. That is the ultimate aim of or advantage of the proposed DC-DC converter. So rather using one source, if you add 2 sources, the overall voltage gain can be improved. That is the main achievement of the proposed DC-DC converter compared to the conventional DC-DC converter. So compared to the conventional approach, you can see what about the losses? Conduction loss decreases, switching loss very low, and inductor loss is also less. So technically speaking, whatever the claim we proposed, that is achieved through the analysis. We said that overall converter efficiency can be improved by reducing the losses. That we have proved here. Similarly, the conventional approach uses 4 switches and we use only 3 switches, 3 inductors and 1 inductor, so that the overall component is also less. So when you try to have the so after completing the steady state dynamic analysis that I am not showing here due to the time constraint, you can look into some of my paper and you can have further detailed studies. So here we have fabricated our proposed DC-DC converter for the level of voltage of 110 volt V1, 72 volt V2, and we have taken 20 kilohertz as the switching frequency. And here you can see the converter performance in terms of V0 and the corresponding inductor voltage. Whatever the shape of inductor voltage I have shown, I think it closely matches in different modes. This is the super boost mode, and this is battery powered mode where V2 alone charges, and here V1 plus V2 charges. Here you can see the inductor. So V1 charges, then V2 charges, then discharges. But whereas here V1 alone, V2 alone charges. Here solar battery mode, here V2 alone charges. Here parking mode means that the excess power is pumped into the utility grid. The excess power is pumped into the utility grid. Then regenerative mode, this is nothing but your buck operation. So you can notice very closely that according to your application, you can decide what is the type of operation can be performed using the proposed DC-DC converter. So that what we have intended here, whatever the conventional DC-DC converter we proposed, the whole thing has been replaced by a multi-input and single output DC-DC converter. We have formulated our research objective effectively. After formulating the research objective, we have achieved those objectives by proposing a new DC-DC converter, and that DC-DC converter has been analyzed well in both steady state as well as in dynamics. After analyzing in dynamics, we have verified the performance of the DC-DC converter in both simulation platform as well as in the experimental prototype. So finally, we have done extensive analysis to prove our claims such as efficient operation, low component, low cost, everything using proper indices. So finally, we have concluded that the conventional approach of integration has been revamped by a monolithic multi-input single output DC-DC converter in the proposed research work. So the outcome of the research work is a novel DC-DC converter with its high improved performance. So as I said, that paper was accepted in IET Power Electronics. I have shown one typical example. So we have another 20 minutes. I will try to complete shortly the dynamic analysis of a DC-DC converter here in one particular mode. This is the steady state analysis. This I already covered. All the state equation I have developed. You can look into this. I have developed all the state equation. I have identified inductor current and capacitor voltage as the state variable. So this is my state variable. So I have taken VL, VC are state variable. I have taken two input voltages as my input variable, and I1, I2 are the two output variable. I am telling you, it depends upon the application. You can select state variable, input variable, output variable. In some application, we take our output variable as the output voltage, sometimes input current. Especially in maximum power point tracking of solar PV, we take your input current as your output variable. Suppose if you are going to regulate the output voltage, you may take V0 as your output voltage. As I already mentioned, everything is depending upon your application. Assume that this is your system. System has state variable something like IL, VC. Apart from that, you have n number of inputs, you have m number of outputs. So from this n number of input and so-called m number of output, you can select which are the input parameters and the output parameters you are interested in that particular application. So in this problem, we have taken I1, I2 are our outputs. So we have formulated our problem like this. So in mode 1, mode 2, we have derived a state equation. Then using state space average model, we have derived average A, B, C, D parameters. Then we substituted the small signal perturbation, something like D is equal to D cap plus capital D. So D cap is your small signal and capital D is your large signal. So after substituting all the small signal and large signal perturbation, we found average small signal model. So from that average small signal model, so finally we have replaced the unnecessary parameters and we found all the significant transfer functions. We set output voltage by input voltage. Yeah, you can see. Output voltage by second input voltage. Yes. VC by D1, D2, two control parameters. So inductor current by V1, inductor current by V2, IL by D1, IL by D2. All sort of transfer functions we have derived from the whole small signal model, and then we have done an extensive study on the stability of the system. As I already pointed out, we have used Bode plot as a tool to infer system stability. So we have drawn the Bode plot and then we computed the phase margin and gain margin. So somebody asked a question, I think Mrs. Sweta asked a question on explain on what basis we can choose the switching frequency. So switching frequency can be designed in control perspective and another one in terms of power perspective. So in control perspective, so according to the phase, I think phase margin and gain margin, you can compute the crossover frequency. With respect to the crossover frequency, you can decide switching frequency in the comfortable zone. So you all know the whole transfer function contain two major constant terms. One is L, another one is C. So I said a transfer function, you can take a transfer function of a system. So here of course I have shown a transfer function. For example, V0 by V1 is nothing but some gain into S plus A whole divided by S plus X into S plus Y. So what is this A, X, Y? These are the constant terms depends upon L and C, which decides the location of poles and zeros. The term L and C decides the location of your poles and zeros. So when there is a disturbance through Nyquist criterion or maybe contour plot, you can predict how the poles and zeros will move either towards stable region or towards unstable region. So according to that, either it goes to stable region or unstable region, you can select your controller. So in order to implement these controllers, you can have your comfortable value of switching frequency. For example, assume that your comfortable switching frequency says 5 kilohertz and above. You can select according to your application and limitations 5 kilohertz. So particularly speaking, application specific. as I said, I have done enough analysis on the given transfer function. I obtained the small signal model. Then I derived my significant transfer functions. Then I proceed towards the selection of controller. So here I have shown the pole zero plot followed by the step response. Now you can see after following an oscillation, the system settled down. So it proves that the system is perfectly stable, but there are sluggish response. So if I would like to go ahead with open loop system, I can go if my application permit. If really you want particular performance, you can go ahead with your controller design. In this work, we have designed a closed loop system for the step change in load. So you can notice how the voltage is getting regulated, though there is a step change in load current. As I said, your reference also will vary according to the application. So here we take V0 as my reference. Sometimes we take IL as a reference. Sometimes we take the average current of source 1, source 2 as our reference. According to your application, you can select what is your reference signal, and accordingly you can go ahead with your controller design. So with this, I have a lot of things, but I don't have time, so that I am coming to the end of my. So thank you very much for giving me an opportunity to share some of my expertise which I developed at NIT Calicut. So with these few words, I stop here. Thank you all of you. If you have any queries in another 10 minutes, I will clarify. Yeah.
Participants, if you have any queries, you can ask.
Sir, good morning, sir. This is Ravi Kumar.
Yes, sir.
I have one question, sir. Sir, if you want to do research on isolated converters in this multi-input type, are there any literature can you recommend, sir? Any particular paper or anything?
Yeah, there are several literature. You can look into IEEE Explorer. Several papers are every issue in power electronics and industrial electronics. They are coming out with isolated converters.
Okay, sir.
There are several papers. Several papers. Yeah.
Okay, sir. Thank you, sir.
Any other questions from the participants?
Any other questions from participants? No other questions. Thank you, sir. Thank you for your wonderful presentation.
Yeah.
I will finish.
There is no other question.
Yes, sir. There is no other questions, sir.
Yeah, you can look into my website. I think most of the papers I have listed. You can see my website so that I have given my detail. So this is my website. When you go to my website, Almost you can visualize all my publications. So someone asked about isolated DC-DC converter. My first paper, that is Sailing System Generator Based Rapid Prototyping of Solid State Transformer for on-grid renewable energy. This is one of the isolated DC-DC converter which we recently published in IEEE Journal of Emerging and Selected Topics in Power Electronics. That paper, you can look into that. And apart from that, we have several publications in IEEE transactions, especially in non-isolated DC-DC converters. In fact, recently also we got 2 papers that is not listed here. One is in IEEE transaction on circuits and systems, and another one is in IET high voltage. So the 2 papers just 2 months back we got. I think one paper already published as a yearly publication. You can look into that. I think the paper may be available here. There I will show you.
Hello, sir.
Yeah, just a minute, please hold. Just a minute.
Okay, sir. Okay, sir.
So this paper we recently published on non-isolated DC-DC converter. So you can look into this paper, how we have explored the advantage of the converter. So this is the topology of our proposed DC-DC converter. You can see how we have explained the operation of the converter in steady state as well as in dynamic, so that you can see how we have done the extensive analysis and then the visible outcome. So like that you can take some of our papers and you can see how we have done the total analysis. Okay. So few papers are not updated here, but most of the papers are updated in this. So you can take some of my papers and you can have your detailed references. Okay, thank you all of you. Hope that let me sign off here so that can go to the.
Sir, one question from the participant.
Yeah.
Sir, one of the Participant has asked that, sir, which journal is good for quick review among SEI journal as per your experience?
Pardon?
Sir, which journal is good for quick review among SEI journal as per your experience?
So in my experience,
Sir, line is on the camera.
so not audible, please.
Hello, sir.
Yeah.
Yes, sir. Yes, sir.
No, what is the question?
Sir, which journal
Huh.
is good for quick review among SEI journal as per your experience?
So in my experience, the paper which I show now, IEEE transaction on circuits and system was very fast. I believe that paper was submitted, I think within 2 months the paper was accepted, I guess. Right from submission to acceptance. It was one of my paper accepted very shortly. But usually IEEE transactions and other journals nowadays they take more than 1 year. I think the detail about communication is not here. I think yeah, it is not here. I think somewhere in the May we submitted this paper and it was accepted in July. So usually in IEEE transaction, if you are lucky enough, your paper will be accepted with the second revision. If there is any delay further, it will go. Every revision they will give hardly 1 or 2 months according to the type of uh, revision you got. If it is major revision, sometime 2 months, sometime 3 months. If it is minor revision, it is 1 month. Like that, it will vary. So, in my experience, the number of paper received by journal significantly increased. And whenever we see a submission of paper, especially in IEEE industrial electronics and power electronics, that too now I'm speaking now September, October. In 2020, of course, some numbers reduced, but whereas last year, the same time, the manuscript number and all more than 4,000. So I don't remember, I don't think reviewing 4,000 journal, wrote 4,000, 5,000 papers in a particular journal, though there are panels of associate editor, etc. I think on an average it may take 1 year in good journals I'm speaking, especially IEEE. If you are lucky enough, sometime paper will come quickly. So depends.
Sir, thank you, sir. One more question, sir.
Yeah.
Sir, one participant has asked, sir, my question is, both simulation and hardware is needed for publication in SEI journals.
No need actually. So even in my experience, I never put simulation result in most of my IEEE transactions. So you can see example as this paper. So in this paper, the total page given me is only 5 pages. So because above 5 pages, you have to pay charges. So each page on an average take 10,000 rupees per page. So we never prefer extending pages because it is costly affair, especially for Indian context. Second one, in the given space, there is a place to keep your simulation result. You can see in this paper, I never keep any simulation result. So, in my point of view, if you will prove your modeling and the other thing in terms of equation, you no need or no reviewer will particularly talk about your simulation result. So in my point of view, simulation is not at all required. Simulation is really spoiling the culture of our researchers. Without doing simulation, if you are sound enough in mathematics, do steady state and dynamic analysis, directly go to the hardware, take hardware result and keep it in the paper, 100% your paper will be accepted. No need of any hardware, no need of any simulation result, no need of even simulation. Don't do simulation first of all. anything else?
Sir, which book we need to refer the modeling of power converters?
Yeah, in modeling of power converters, there are different textbooks available nowadays. E-books are there. In my experience, I think there is a professor called Professor Umanand from IIC Bangalore. Sir has written many textbooks, particularly I think modeling and simulation of power converters. Narosa publishers, I think. I could not recognize exactly. You can search it in Google, otherwise you can go to SAR's website, Umanand Sir website in IIC Bangalore. I think his textbook, I found one of the good textbook, especially in modeling perspective. Otherwise, you can take Rashid Sir book, any standard power electronics book, but they may not explain in depth. They may not explain in depth. Okay, it depends. It depends. So that's what I'm repeatedly telling. If you want to become a master in power electronics, and that too, if you would like to publish papers in IEEE transactions, you concentrate highly in dynamic model. So nowadays, any paper they are asking dynamic model, and that you can show as one of the contribution. Okay, that is the merit of showing the dynamic. For whatever the dynamic model I have shown, that is only developed by me for the proposed converter. That is nowhere available. That is one of the significant contribution you can highlight in front of the reviewer.
Okay, sir. Hello, sir.
Yeah, I'm hearing. Yeah.
Yes, sir. Yes, sir. Further, there is no questions, sir. So we can wind up the session, sir.
Yeah. Thank you.
Thank you,
very
sir.
much for
Thank
the
you for.
opportunity provided. Yeah. Thank you. Thank you all of you.
Okay, sir. So shall I